press the bell icon on the YouTube app and never miss another update.
Today we are going to discuss electromagnetic waves. Now to start with, let us take introduction to electromagnetic waves. Now before going to discuss actually electromagnetic waves, we need to understand many concepts, right? For example, Maxwell's equation, displacement current, etc. Now the displacement current is the new term or new type of current we are going to use in this chapter. So far we have discussed electric current, right? Now the rate of flow of electric charges across a section of a conductor is called electric current. Now this electric current is due to the flow of free electrons through a metallic conductor under a constant potential difference or applied electric field. When electric field is applied to a conductor, a potential difference is established across the ends of the conductor under the influence of electric field, right? Free electrons are flowing from lower potential to higher potential, and the conventional current flows from higher potential to lower potential, right? Now for the sake of convenience, this electric current flowing through a metallic conducting wire, right, is called as conduction current, and now onwards that conducting current is denoted by IC, right? Conducting current, right? Conduction current means it is the current flowing through a metallic conductor due to the flow of free electrons under a potential difference. Now another thing is, we have also discussed, right, magnetism, right, and now we are entering electromagnetism, right. Now according to H.C. Oersted, now we will take it one by one. Now according to H.C. Oersted, that is Hans Christian Oersted, a current carrying conductor produces a magnetic field around it, right? Suppose we have a conductor AB, right, and no current flowing through this conductor. When we place a magnetic needle here, magnetic needle means a magnetic compass box. It is used to detect the presence of a magnetic field in a region. When a magnetic field is kept in, magnetic compass box or magnetic needle is kept in a region where there is no magnetic field, external magnetic field, but Earth produces magnetic field. Now that magnetic needle comes in the direction of Earth's magnetic field, approximately along the north-south direction, right? Now there is no deflection in magnetic compass box. Now whenever through the same conductor AB, when we pass a current I, now the compass box or magnetic needle shows deflection in one direction. That indicates that whenever a current flows through a conductor, a magnetic field is produced right around the conductor. right? And this effect is called magnetic effect of electric current, and it is discovered by H.C. Oyster. That means a current carrying conductor always produces a magnetic field around it. And when we go on increasing the magnitude of electric current, now the magnitude of deflection increases. That indicates that there is an increase in magnitude of magnetic field, right? Just like electric field, magnetic field is also, right, a vector quantity having both magnitude and direction. Now, when we reverse the direction of current in the conductor, the direction of deflection also gets reversed. That indicates that the direction of magnetic field get reversed in that region. And this effect is called as a magnetic effect of electric current, right? And it is discovered by H.C. Oyster, right? Now at this stage, we know a current carrying conductor produces electric field, right? It is around 1860, right? He discovered this effect. Now, there are two laws for obtaining expressions for magnetic field due to a current carrying conductor. Now, we know that electric field is the region of space around a charge where other charges experiences a force. In a similar way, magnetic field is the region of space where another magnet or a moving charge experiences a magnetic force, right? Now, the magnetic field due to a current carrying conductor can be calculated by number one, it is Laplace Law, right? We know that the Laplace Law is also called as Biot-Savart's Law. It gives the magnitude of magnetic field at any point due to a current element, right? According to this law, right, magnetic field due to current element dB is equal to mu naught over 4 pi, right, mu naught over 4 pi ideal sine theta by r square, where that term product ideal is called as a current element, right? Mu naught over 4 pi is a proportionality constant used in magnetism, just like 1 over 4 pi epsilon naught is a constant in electrostatics, right, in free space. This is also a constant in free space, that is air or vacuum. Using this, we can find the magnetic field due to a straight conductor carrying current, a circular conductor carrying current, or a conductor of any shape. Another law which we are going to use is Ampere Circuital law. This is very important here. Ampere's Circuital law. Now, according to this law, right, now, or we take the statement of this law, right, the line integral of magnetic field around a closed path is always equal to, right, mu naught times the current enclosed by the closed path in free space, right. So, mathematically, that line integral of B dot dl is equal to mu naught into I, right, where I is electric current, mu naught is right, a permeability of free space, dl is a small elementary length of the loop, and B is the magnetic field at the point, right. Suppose we are having, right, so many conductors, right, a carrying current, say I1, this is I2, this is I3, etc., right. perpendicular to the plane of the board, outward or inward. Suppose we are having a closed path, right, that enclosing the current, right. Here that current, say I3. Now this current I is equal to I1 minus I3 plus minus I2 plus I3. Now if we take any elementary length, this dl vector, and the magnetic field is B, which is along the tangent drawn to the closed path at any point, right, then B dot dl vector is equal to mu naught I. Suppose if we have a straight conductor carrying a current I, suppose at any point, say P, to find the magnetic field at this point, let us consider a circular loop of radius R. Then the magnetic field at this point B is given by B into integral of dl, length of the entire loop, it is equal to 2 pi r is equal to mu naught I, or B is equal to mu naught I by 2 pi r. So we have derived this relation, that is magnetic field at any point near a straight conductor carrying current, and according to Ampere Circuital law, it comes out to be B is equal to mu naught I by 2 pi r. This is the Ampere's Circuital law. We are going to discuss in detail about this Ampere's Circuital law. Now, the third thing is, right, electromagnetic induction or EMI. Now, Faraday discovered the phenomenon of electromagnetic induction. According to Faraday, whenever there is a change in a magnetic flux linked with a coil or a circuit, right, an EMF is induced, right, in the coil or the circuit, and this effect or phenomenon is called as electromagnetic induction. And suppose if the coil or circuit is closed, a current is induced in the circuit, and that current is called as induced current. The EMF is called induced EMF and the current is called induced current. Now, the magnitude of induced EMF in the coil is given by, it is d phi b by dt, where d phi is the change in magnetic flux linked with the circuit, right, and dt is the time taken. This d phi by dt represents the rate of change of, right, magnetic flux linked with the coil. In fact, this is Faraday's second law, right, and we know that what is an induced EMF or generally EMF? It is the amount of work done, right, in driving a charge once round a closed circuit. As we have discussed in electric current, EMF is equal to, right, it is work done by charge. And we also knew that electric field is equal to, right, potential difference by length. That is, whenever there is an EMF is induced, it means that an electric field is induced, right. So the result of electromagnetic induction is that a changing magnetic field induces an electric field. It induces electric field. So far, we know that, right? A current carrying conductor produces an magnetic field, and here, according to electromagnetic induction, a changing magnetic field induces or produces an electric field, right? Now, keeping in mind, right, these three concepts: one, magnetic effect of electric current; number two, Ampere Circuital law; and number three, right, EMI, a changing magnetic field induces an electric field, right? Now, the fourth point of our discussion is, now it is clear that a conduction current, that means current flowing through a conductor, produces a magnetic field. Right. On the other hand, from electromagnetic induction, a changing magnetic field produces an electric field. These two are experimentally established facts. Now the question is the reverse true? Right? Is the reverse is true? That means can a changing electric field produces a magnetic field? Now the question is, can a changing electric field produce a magnetic field, right? Now this is the earlier discussion, right, nearly about at 1860. Now this is the question that has arrived, right, because of these two facts. Now the answer to this question is given by James Clerk Maxwell, right? So answer is given by James Clerk Maxwell, right? Now according to him, a time varying electric field, that is an electric field which is changing with time, gives rise to a magnetic field, right? To establish this fact that a changing electric field produces a magnetic field, he conducted an experiment, right? Now he conducted an experiment, right, by charging a capacitor, right, where he is finding magnetic field outside the capacitor and magnetic field inside the capacitor, that is between the plates of two charged capacitor, right? Now according to Ampere's circuital law, right, there is no magnetic field, right, inside the plates of the capacitor, right? This is accordance with Ampere's circuital law. But how to detect the presence of magnetic field there? Whenever the capacitor is charging or discharging, if we keep a magnetic needle between the plates of the capacitor, that shows right deflection, indicating that there is a magnetic field. When capacitor is uncharged or when capacitor is completely charged, the magnetic needle shows no deflection. That means to say, when we observe by placing a magnetic needle, as long as the capacitor is charging or discharging, there is a magnetic field, And now, according to Ampere's circuital law, this magnetic field inside the capacitor is 0, Now, but exists outside the capacitor due to the flow of electric current through the connecting wire. Now, this Maxwell found an inconsistency, in Ampere's circuital law when it is applied to a circuit which is containing a capacitor, This inconsistency in Ampere's circuital law leads Maxwell's to apply a correction to Ampere's circuital law, and more important thing, he formulated Maxwell's equation, which completely describes the electromagnetic phenomena, that gives the relation between electric field and magnetic field, and he also discovered electromagnetic waves, Now, fifth one, we will take that one. Another thing. So far we have discussed capacitor and charging of a capacitor, but here we need to know, or more correct to say, let us recall the process of charging of a capacitor, Now, let us consider a parallel plate air capacitor, say having the plates P and Q, an uncharged capacitor. How to charge a capacitor? A capacitor can be charged by connecting it to a battery. Now, it is connected to a battery, and a key. When the key is closed, now the positive potential at the point plate P pulls out an electron and transfers this electron to the plate Q through the external circuit, that is through the connecting wire, So, when an electron arrives at Q, it becomes negatively charged. Due to the loss of electron, plate P becomes positively charged. Now, the charge is transferred from one plate to another plate. That means there is a displacement of charge from one plate to another plate, of course, through the conducting wire. Now, there exists a potential difference between the two plates. One is at positive potential and at negative potential. But still, this is at positive potential and this is at negative potential due to the battery. Now, again electron, comes from plate P to plate Q. As a result, negative charge on the plate P increases, positive charge on the plate, negative charge on the plate Q increases, positive charge on the plate P increases, Now, this process is called as charging of a capacitor. Now, the amount of work done in charging the capacitor is stored as electric potential energy in the form of electric field. Now, the thing is, whenever electron is flowing from plate P to plate Q, a current flows through the external circuit, and that current is called as conduction current, Now, as the charge on the capacitor goes on increasing, right? Now the value of conduction current goes on decreasing. When this capacitor is charged to battery potential, right? It is completely stored the charges. Then there is no potential difference between plate P and the battery, right? Therefore, there is no further flow of electron from P to Q. We say that, right? Now the capacitor is completely charged, right? So when the charge here between the plates increases, there is an electric field between the plates, right? Electric field between the plates of the capacitor. E is equal to sigma by epsilon naught, right? Now this E is equal to sigma, that is Q by A into epsilon naught, where Q is the charge, right, on the plates of the capacitor, and A is area of the plates, which we have derived, right, while studying capacitor. Now the thing here is, as the charge increases, the electric field also increases. That means during the charging of the capacitor, right, the charge on the plates of the capacitor increases with the time. At the same time, the electric field also increases with the increasing time, or it increases with the time, and that electric field can be called as a time varying electric field. There is a rate of change of electric field with respect to time, right? So when capacitor completely charged, this conduction current becomes zero, right? Now with these points, right, we will discuss, right, Maxwell's correction to Ampere Circuital law, that is modified Ampere Circuital law, and it is called as Ampere Maxwell's Circuital law. Ampere Maxwell's Circuital law, right? To understand these things, right, we have to understand, or we should know the concepts which we have discussed earlier, right? With that fact, right, we will move on to that one, and now we will take, according to Ampere Circuital law, right, the line integral of magnetic field over a closed path in free space is equal to mu naught times the current enclosed by it. Mathematically, line integral of B dot dl is equal to mu naught I, right, where I is current, and of course it is the conduction current, right? Now this is equation 1. Now Maxwell's, right, conducted an experiment, right? Now that experimental arrangement consists of two plates of capacitor P and Q connected to a battery and a key. When the key is closed, right, an electric current, right, starts flowing through the circuit, and that current what we call here as a conduction current, current flowing through the connecting wire. Now as a result of which the plate Q becomes negatively charged and plate P becomes positively charged. Now as the current, as the charge on the plates increases, the conduction current decreases. It is a time varying current that is flowing through the circuit, right? And when capacitor is completely charged, the conduction current becomes 0. Now, let us consider a point R outside the capacitor at a perpendicular distance R from it. Now let us consider a circular loop of circumference or length is equal to 2 pi R. Now there is a magnetic field B here. Now according to Ampere's Circuital law, right, this line integral of B dot dl is equal to mu naught into IC, where IC is the conduction current, or B dl cos theta is equal to mu naught IC, right? Now as theta is equal to 0 degree, because the magnetic field is always along the right tangent, right, drawn to the loop at that point, that is along the direction of dl vector. Therefore B into, right, integral dl vector will be cos 0 degree is equal to 0, integral of dl is equal to length of the right loop, that is 2 pi r is equal to mu naught IC. Now B is equal to mu naught IC by 2 pi r. Let us take it as equation 2. So according to equation 2, right, the magnetic field at point R outside the conductor is 0. Sorry, not 0. B is equal to mu naught IC by 2 pi R. Now let us take the second part of it, right? Remember that is equation. Now that B is equal to, right, mu naught I by 2 pi R, that is equal to equation 2 at point R outside capacitor, right. Now the same thing, right, if we consider a tiffin box shaped surface, yes, right, without a lid, right, that is when you open a tiffin box, circular tiffin box, right, then one side is a circle and another side is a plane surface, right. Now we will consider here like this. This is the surface, yes, here. Now this surface is neither in contact with the connecting wires nor in contact with the plates of the capacitor, right. It lies in a free space. Now let us find a point R dash here, right, electric field at this point. Now this is the, say, it is a loop C, right. Now to find magnetic field inside that one, right, say at the point R dash, right, we can take this point R dash, right. Now here according to Ampere Circuital law, no current inside the capacitor, that means no conduction current inside the capacitor, right. Therefore the surfaces encloses no current. Now using this integral of B dot dl is equal to mu naught into IC, or integral of B dot dl, right, is equal to mu naught into 0, that is equal to 0, because there is no conduction current in the region between the plates. IC is equal to 0. That means the magnetic field, right at any point R dash, right, inside the capacitor is 0. Let us take it as equation 3. At this is R dash inside capacitor. At R dash inside capacitor, right? Now the magnetic field inside the capacitor. If they take equation 2 and equation 3, we are considering. That means outside the capacitor there is a magnetic field. Inside the capacitor there is no magnetic field, right? So, according to Ampere Circuital law, the magnetic field inside the capacitor is 0. There is no magnetic field. But when we place a magnetic needle, right, during the charging or discharging of the capacitor, that shows deflection, indicating that there is a magnetic field between the region of two plates, right? Here, Ampere's circuital law fails to find, right, give magnetic field between the plates of charging or discharging capacitor, right? So, Maxwell's, right, argued that, right, Ampere's circuital law is logically inconsistent, right? It cannot be applied, right, completely to a circuit, electrical circuit that contains capacitor. Is that clear? According to Ampere circuital law, outside the capacitor there is a magnetic field which is given by the equation 2. Inside the magnetic field, right, according to the same law from equation 3, it is equal to 0. Now, Maxwell, suggested that there is an inconsistency in Ampere's circuital law, right? Now, according to him, this inconsistency is due to a missing factor, right? Now, what is that missing factor, right? Now, here that missing factor is a displacement current or the rate of change of electric field, right? Now, listen carefully. Now, we are going to introduce according to Maxwell, right? He introduced the concept of displacement current, right, to find the magnetic field between the plates of the capacitor, right? Now, according to Maxwell, right, whenever the capacitor gets charged, right, there is an electric field, right, that increases during the discharging of the capacitor and decreases during the discharging of the capacitor. When the capacitor is completely charged, right, there is no change in the value of electric field, that remains constant here. Suppose at any instant of time, let Q be the charge on the capacitor, right? Let Q be charge on capacitor during the charging of the capacitor, right? Then there is an electric field between the plates of the capacitor, right, which is perpendicular to the surface S, bottom surface S of the Tiffin box shaped surface, right, perpendicular to the surface, that is it is from positive plate towards negative plate. This is the direction of electric field here. Now that electric field E is equal to, right, sigma by epsilon naught. where sigma is surface density of charge, right, and epsilon naught is permittivity. Suppose if A is area of cross section of the plates, then this is equal to, right, Q by A into epsilon naught, right. Let us take it as equation number 4. Equation number 4 gives that electric field, right, or this electric field, right, is changing with respect to time, right. Now, according to this electric field, the flux between the plates of the capacitor, or the electric flux passing through the surface, remember that electric flux is the number of, right, electric lines of force passing normally through a surface in an electric field. That phi E is equal to, that is E dot A, that is equal to E A cos 0 degree, because the direction of electric field and the direction of electric vector are the same. Therefore, angle between area vector and electric field is 0, right, and cos theta is equal to 0, and this is phi E is equal to, right, EA. Therefore, that electric flux passing through the surface S is equal to, right, this is electric field E is Q A by A into epsilon naught, right, or phi E is equal to Q by epsilon naught, right. Now, the instantaneous charge, now instantaneous charge on the plates of the capacitor Q is equal to epsilon naught phi. We know that during the charging of the capacitor, the charge on the plates increases. During the discharging of the capacitor, the charge on the plate decreases. Now here we see that, now if dq by dt is the rate of change of charge on the plates of the capacitor, then this dq by dt is equal to epsilon naught into d phi E by dt. So dq by dt is equal to epsilon naught into d phi E by dt, right. Now this dq by dt, the rate of change of charge in the plates of the capacitor is called conduction current, displacement current, and it is denoted by ID, and this is called displacement current, right. So therefore, displacement current that is flowing in the region of space between the plates of charging capacitor, ID is equal to, right, epsilon naught d phi E by dt. Right. So the displacement current ID is equal to epsilon naught into d phi E by dt. This current, the name displacement current is given by Maxwell. It is because of the fact that here epsilon naught into d phi E by dt, this term, right, epsilon naught into d phi E by dt has dimensions of current. It has dimensions of current, that is m0, L0, T0, a to the power of 1, right? Therefore, this ID is nothing but an electric current, but it is not the conduction current. This current ID is not due to the flow of charges through a conducting wire. In fact, it is due to, right, the change in electric flux, right, between the plates of the capacitor or through a surface which is placed between the plates of the capacitor, or due to the change in electric field with respect to time, or due to the rate of change of charge across the plates of the capacitor, that is dq by dt. So here dq is the charge, right? Here in capacitor, while charging, the charges are transferred from one plate to another plate. That means there is a displacement of charge from one plate to another plate. Therefore, this current ID, right, is called as displacement current. And this displacement current is completely different from conduction current, right? The conduction current is due to the flow of electric charges through a conducting wire, that we generally called as electric current. But the displacement current, right, arises due to the rate of change of electric field or the rate of change of electric flux in a region, right, and that is displacement current. Now, it is clear that there is a current flowing between the plates of the capacitor due to the rate of change of electric field, right? Now, Maxwell has applied a correction to this law, right? Now, according to Maxwell, Ampere's circuital law can be written as line integral of B dot dl is equal to, it is right, the sum of conduction current and displacement current, IC plus ID, right, into mu naught, or we can more quickly see. So this is mu naught into IC plus ID. Right, this is the missing term in the Ampere's circuital law that made Ampere circuital law, right, inconsistent, logically inconsistent. Now, or this law can be written as line integral of B dot dl is equal to mu naught into IC plus mu naught into IC, mu naught into IC plus what is ID? Epsilon naught d phi E by dt. Right. So this is the modification, right, applied by Maxwell's to the Ampere's circuital law, and this law is called Ampere Maxwell's circuital law. So here the important thing here is the concept of displacement current introduced by, right, Maxwell to correct Ampere circuital law, and this law is applicable to, right, all the circuit, right. If a circuit contains a capacitor, then there will be a displacement current ID. Suppose a circuit contains no capacitor, then there is only conduction current. There is no displacement current, right? Now this becomes, right, ID is equal to 0, and that becomes Ampere Circuital law. Line integral law of V dot dl is equal to mu naught into IC, right? And this is the modification, right, of this Ampere's Circuital law. Now we'll take displacement current, that is ID. Now the current that exists in a region of space due to the change in electric field or the change in electric flux in that region is called as displacement current. A current that arises due to change arises in a region, that arises in a region due to change in electric field or electric flux is called, right, displacement current. Is called displacement current. Now the displacement current is given by ID is equal to, right, epsilon naught into d phi E by dt, where epsilon naught is absolute permittivity of free space and d phi E by dt is the rate of change of electric flux, right? Now the displacement current is not the conduction current, right? Displacement current, right, flows in a region where there is a rate of change of electric field or electric flux. Conduction current flows through a wire where there is a flow of electric charge, right? Now this conduction current IC and displacement current ID are individually discontinuous, right? But when they exist in two different part of a circuit and they make continuous, and if there are conduction current and displacement current at different parts of a circuit, then the total current in the circuit is IC plus ID. IC plus ID is continuous. IC and ID are individually discontinuous, right? So generally displacement current exists only when there is a change in electric field, right, with respect to the time. If there is no change in electric field with respect to time, then there is no electric field. For example, if we have a charged capacitor, completely charged capacitor, right? Now there exists an electric field here. This electric field is equal to sigma by epsilon naught is equal to constant. There is no change in electric field with respect to time, as there is no change in the charge in the two plates of the capacitor, right? In that case, the magnetic field inside the plates of the capacitor is zero. Obviously, right, ID is equal to 0 because this d phi by E by dt is equal to 0, right? And this displacement current that produces a magnetic field. Now, in the introduction, we are taking the point number 5. According to electromagnetic induction, a changing electric field, a changing magnetic field produces a constant electric field. The question was, can a changing electric field produce magnetic field? The answer is yes, right? When a capacitor is charging or discharging, as an example I am taking, there is a change in electric field with time between the plates of the capacitor, and that changing electric field with respect to, right, the time give rise to a constant magnetic field, right? So both are reversible. A changing magnetic field gives rise to a constant electric field. A changing magnetic field gives rise to a constant electric field according to EMI, but according to Maxwell, a changing electric field gives rise to a constant magnetic field, right? And this experiment of Maxwell's, right, to modify Ampere Circuital law leads to a very, very important discovery, that is electromagnetic waves, right? In the next class, we will see, right, how electromagnetic waves are generated and what made, right, Maxwell's to predict electromagnetic waves in the year 1884. Right? Okay, we will continue in the next class.